Today we're going to talk about power in electrical circuits. Power is defined as the rate at which work is done, but I find that definition not very helpful for the imagination, so I would rather think of it as the rate at which energy is transformed from one kind to another. Because remember, work is just how much energy has been changed from one kind to another, right? Change in energy, that's how we've defined it before. So let's think about an example of some context that you know power from. So let's say your car. So usually the power output of the engine is measured in horsepower, and the faster an engine can transform chemical energy from your gasoline into kinetic energy that moves your car, the higher the horsepower of your car will be, or the heavier things it'll be able to tow, right? So that's one application of power. Or in an electrical context, if you take electric potential energy and want to change it into light, let's say you'd use a light bulb, and back when we were using incandescent bulbs, then light bulbs were measured in like 100 watts or 60 watts or 40 watts. And the higher the wattage or the power of the light bulb, the brighter it would be, right? Because it's transforming electric potential energy into light. And the faster it can do that, the brighter your light bulb will be. So power is the rate at which energy can be transformed from one kind to another. And we're going to talk specifically about changing electric potential energy into something else, whether it's sound or light or heat or what have you. So we can define power using a formula or an equation as well. P equals W over T. Okay, and we can just label those things to make it a little bit more helpful for your notes. W is work, and remember that's change in energy, so that's measured in joules. T is time, and it's measured in seconds, as it always is, and P is power. So if we look on the right side of the equation, you've got joules per second, right? Energy transformation per second. So power can be measured in joules per second, or the standard unit would be watts. You could also measure it in horsepower. You could just convert your watts to horsepower. So that's the first part. We're defining power as energy transformation per time. We want to connect it, though, to those other characteristics of circuits that we've been working with so far. So voltage, current, and resistance. So the one we're going to start off with, let's go back to green. The one we're going to start off with is P equals IV. Now, I'm not going to derive that for you from scratch, but we are going to do a unit analysis that hopefully is going to give you some confidence that that's true. So let's think about I times V. So current is measured in amps, right? And voltage is measured in, what is it again? Oh yes, volts. Amps and volts, though, can be broken down further to make this make a little bit more sense. So amps is coulombs per second. Volts is joules per coulomb. And now maybe you can already see what's going to happen here. So we've got coulombs on the top of the left-hand unit, and we've got coulombs on the bottom of the right-hand unit. And so we can actually just cancel both of those coulombs out, and you can see that that leaves us with joules per second, watts, exactly what we were expecting. So P equals IV, the units work out exactly how we would expect. So you can calculate the power output of any component of a circuit or the circuit in total using the current and the voltage of either that component or the entire circuit altogether. So now we're going to connect P equals IV to the other characteristics of circuits that we know, the V equals IR. So let's start off with P equals IV and V equals IR. And so we're going to take this IR part that's equal to voltage, and we're going to sub it into the P equals IV formula right over there. So now this becomes P equals I times IR. And we can make that better. So the version that we're going to use is P equals I squared R. Okay, so that's a version of power that only uses current and resistance to calculate it. But that's not the only thing that we can do. We can start off with P equals IV again, but let's use a different version of V equals IR. Let's put I by itself. Okay, so we've got I equals V over R. And now we can take that V over R part and sub it into the I spot in power. And so now you get P equals V over R times V. And again, we can make that better. So P equals V squared over R. And those are the different relationships between V, I, and R with power included. Now let's try a couple examples. A 400-watt electric heater draws a current of 5 amps. What is the resistance of the heating coil in the heater? So we're given power, 400 watts, we're given current, and we're looking for resistance. Okay, so this is going to direct us to the correct version of a power formula to calculate the thing that we're looking for. So we're looking for R. We have power, 400 watts. We have current, 5 amps. And so because I'm trying to relate P, I, and R, I want to use the version of the power formula that has P, I, and R in it. So P equals I squared R. Now I'm looking for the R part, right? So R is going to be equal to P over I squared. Then we can put in the numbers. So 400 watts divided by 5 amps. Remember to square it. And R is 16 ohms. So that version of a problem involving power is really just about identifying which version of the power formula you will actually want to use to calculate the thing that's missing. The other version that we could do is a little bit more involved. So here we go. A 6-volt battery is connected in series to a 2 ohm resistor. How much heat does the resistor produce in 1.0 hours? How much heat does the resistor produce? Okay, so we've not been asked about something like this before. We didn't really discuss what that could mean previously in this lesson. So let's remember that heat is just a type of energy, right? So this is asking us how much electric potential energy is being changed into heat in 1 hour. So it's looking for change in energy, right? How much electric potential energy is being changed into heat. That's also known as work. Okay, so what we're actually trying to do in this problem is calculate work. Now, when I look at the things I have voltage. So first of all, I'm looking for work, right? That's my end goal. I'm given voltage is 6 volts. I'm told this is connected in series to a resistor. That's actually immaterial for this particular thing because we're just looking for the heat produced by that resistor, not a whole circuit. Then whether it's connected in series or parallel would make a difference. But in this case, we're just looking for the power output of one particular component. So this is also resistance, 2 ohms. That's also given to us. And we're looking for the heat produced in 1 hour. So that's time. It's 1 hour. So I don't have a formula that's going to do in one step this whole thing, right? Work, voltage, resistance, time. So I'm going to think about going from the end to the beginning. So if I wanted to calculate work, and this was involving energy usage, resistance, voltage, time, probably I'm going to end up using P equals W over T, right? That's probably going to be my ending step, given that I'm given time. I just don't have power yet. And so that gives me a clue about how to begin this problem. I probably need to figure out power using voltage and resistance, right? So then my step 1 of this is going to be P equals V squared over R. So once I've calculated power, Then I can use that power in the second step, the P equals W over T, and then we can finish solving for work. But let's start with power equals V squared over R. V is 6 volts. We're going to remember to square that, divided by R, which is 2 ohms. 6 squared is 36, divided by 2 is 18 watts. Okay, so the power output of this one resistor is 18 watts. So now I've got power. Now I can solve for that W term. So I'm looking for W, and so that's going to be PT. Work is equal to 18 watts times, okay, now remember that time needs to be measured in seconds, right? So I need to actually take this 1 hour over here and recall that 1 hour is 3,600 seconds. Now, if this wasn't 1 hour, if it was a different time, like 1.34 hours or something like that, I'd actually have to do a whole conversion there, right? But in this case, I know that 1 hour is 3,600 seconds. So 18 watts times 3,600 seconds, and that gives me a work of 64,800 joules. Now there's context to this question, right? It's asking me for how much heat was produced. So to make this a really good answer, I would want to say that work equals 64,800 joules. Great. 64,800 joules of heat were produced. And that's the end.